Greetings. In this video, we are going to discuss Deep Feed-Forward Neural Network in machine learning. First, we will talk about neural network-based machine learning. Neural network-based learning, or deep learning, is a subset of machine learning that uses artificial neural networks to model and solve complex problems. Neural networks comprise multiple layers of interconnected nodes, or neurons, that process information and extract features from the input data. Neural network-based learning has become increasingly popular in recent years due to its ability to learn and recognize patterns in data, even when the data is highly complex or nonlinear. It has been successfully applied to various applications, including image recognition. During training, the neural network adjusts the weights and biases of its neurons to optimize its performance on a specific task. The training process typically involves forward propagation, where input data is passed through the network and output is generated. Backpropagation, where errors in the output are propagated backwards through the network to adjust the weights and biases. Now, we will discuss basic concepts of Deep Feed-Forward Neural Network. A Deep Feed-Forward Neural Network, also known as a multilayer perceptron, MLP, is an artificial neural network consisting of multiple layers of interconnected nodes, each processing the previous layer's output. It is called feed-forward because the information flows in one direction, from the input to the output layer, without loops or feedback connections. In a deep feed-forward neural network, each layer of nodes performs a transformation on the input data, which is then passed to the next layer. The input layer receives the raw data, and each subsequent hidden layer applies a nonlinear activation function to the previous layer's output. The final layer produces the network's output, a scalar value, a vector, or a set of probabilities for classification tasks. The term deep refers to the fact that deep feed-forward neural networks can have many hidden layers, enabling them to model complex relationships and learn high-level abstractions from raw data. However, training deep neural networks can be challenging and requires advanced optimization techniques such as backpropagation and gradient descent to adjust the weights and biases of the network's parameters during training. A feed-forward neural network approximates functions in the following way. An algorithm calculates classifiers using the formula y equals f, x. Input x is therefore assigned to category y. According to the feed-forward model, y equals f, x, theta. This value determines the closest approximation of the function. Feed-forward neural networks serve as the basis for object detection in photos, as shown in the Google Photos app. Now it is the time to know about the working method of Deep Feed-Forward Neural Network. When the Deep Feed-Forward Neural Network gets simplified, it can appear as a single-layer perceptron. This model multiplies inputs with weights as they enter the layer. Afterwards, the weighted input values get added together to get the sum. As long as the sum of the values rises above a certain threshold, set at 0, the output value is usually 1, while if it falls below the threshold, it is usually -1. Now, we will talk briefly about the layers of Deep Feed-Forward Neural Network. Input layer. This layer's neurons receive input and pass it on to the other network layers. Feature or attribute numbers in the dataset must match the number of neurons in the input layer. Output layer. According to the type of model getting built, this layer represents the forecasted feature. Hidden layer. Input and output layers get separated by hidden layers. Depending on the type of model, there may be several hidden layers. There are several neurons in hidden layers that transform the input before actually transferring it to the next layer. This network gets constantly updated with weights to make it easier to predict. Neuron weights. Neurons get connected by a weight, which measures their strength or magnitude. Similar to linear regression coefficients, input weights can also get compared. Weight usually is between 0 and 1, with a value between 0 and 1. Neuron. Artificial neurons get used in feed-forward networks. Neurons function in two ways. First, they create weighted input sums, and second, they activate the sums to make them normal. Activation functions can either be linear or nonlinear. Neurons have weights based on their inputs. During the learning phase, the network studies these weights. Activation function. Neurons are responsible for making decisions in this area. According to the activation function, the neurons determine whether to make a linear or nonlinear decision. Since it passes through so many layers, it prevents the cascading effect from increasing neuron outputs. An activation function can be classified into three major categories: sigmoid, tanh, and rectified linear unit, ReLU. Categories of activation function. A. Sigmoid. Input values between 0 and 1 get mapped to the output values. B. Tanh. A value between -1 and 1 gets mapped to the input values. C. Rectified linear unit. Only positive values are allowed to flow through this function. Negative values get mapped to 0. Now, it is time that we understand the math behind deep feed-forward neural network. Typical deep learning algorithms are neural networks, NNs. As a result of their unique structure, their popularity results from their deep understanding of data. Neurons are hexagons in this image. In neural networks, neurons get arranged into layers. Input is the first layer, and output is the last, with the hidden layer in the middle. NN consists of two main elements that compute mathematical operations. Neurons calculate weighted sums using input data and synaptic weights, since neural networks are just mathematical computations based on synaptic links. In a matrix format, it looks as follows. In the third step, a vector of ones gets multiplied by the output of a hidden layer. It is time to see the practical usage of it in daily life. Deep feed-forward neural networks solve problems that require pattern recognition. For example, a neural network could be trained to recognize handwritten digits. Another example is the Google self-driving car, which is trained to classically recognize a dog, a truck, or a vehicle. They are suitable for pattern recognition, classification and optimization. This includes handwriting recognition, face recognition, speech recognition, text translation, credit card fraud detection, medical diagnosis and solutions for vast amounts of data. It can be used to find links between patterns, convert one type of data to another and make associations or generalizations between different entities. Thank you for being a good listener.